готовность материала, чтобы выдавать заданную форму готовым уже изделием. Далее также был разработан технологический процесс, это получение больших листов функционального композиционного материала, так называемый боралюминиевый композиционный материал.
Можете переводить, я буду с вами здесь видео находиться. Да. Да, вас должно быть слышно. Начните с удобного момента, потом.
Процесс является нестабильным, особенно при выражении границы. Потом эти результаты были определены на различных композициях с различными режимами получения материала. В итоге
So if we can count and manage the characteristics at the edge, it means that we can also make the opposite task. And we can realize the processes that interest us. So it was realized with the help of different processes of rolling, when we can manage the core of the deformation, and we can reduce the rolling efforts, bringing it back to the better characteristics and possibilities, which is connected with the deformation of instrument steel. With the apply of this kind of approach, the instrument as a rolling machine was composite. And these approaches, including, they led to realize the process of pressing of higher transmissions. Consequently, the general approach that was used on polymer materials as well as on aluminum materials and metal materials, the next task is analysis of behavior materials, which contains both components. When we have polymer fillings of plastins with layers and some metal layers. But we also have a different task where there is a common solution and the analysis of material behavior. It's medicine. The question of augmentation of different defects. So basically they are widely used in general medicine. It's some kind of biomimetics which we can print, for instance, and it can replace natural fabrics, and it has a geometrical ingredient and non-heterogeneous side of the net. And while pressing, we receive a non-linear behavior. With a cycle loading, this destruction has brighter characteristics, and separate cells can even crack. At the same time, testing of these patterns is not really proved, and doesn't truly model the environment derived when the fabrics are formed. And the solutions can differ essentially. So we have shown that there is a strong influence in printing in technology. And there are different deformations. Let's call it the natural environment of material life. So we also went to the hydrogel materials, which is an essential component of engineering and fabrics. These kind of materials can also be as a porous body that imitates the micro surrounding of the texture. And the promising tasks that we are solving at the moment, it's about the process of destruction of materials under influence and under employment. It's both about polymeric filling as well as metal fillings. So coming to the consequences concerning the questions of material behavior is a very relevant question, and the methods and approaches researched led us to create a range of technological processes concerning materials with different components, as well as shown some promising approaches. This is all, thank you. The results that your team has received, and you were talking about micro and meso, and when you were talking about micro, the mechanisms were a little bit hidden. Could you please tell us a little more about this work and what is included in the micro layer stage and what tasks you solve? So we have two stages, it's micro and meso. At the meso stage, we researched the heterogeneous environment.
Все сработало? Подождите. Так, сейчас мы...
Иван Сергеевич, когда вы говорили о материалах ячеистых, метаматериалах, вот, или как их еще называют, которые для, я так понимаю, замещения элементов костного скелета, да?
Ну, вот
Во-первых, из каких материалов вы это печатаете или собираетесь печатать?
Эта работа выполняется совместно с Уральским федеральным университетом и медицинской академией. Они уже печатаются. Я работаю в том числе не только с геометрией формы кубика, это для наглядности, а так называемая персонифицированная медицина, когда печатается готовое изделие и стоит задача анализа его возможного поведения, нагрузки, которые он будет выдерживать на протяжении какого времени. Там мы работаем уже с более сложными. Печатается это из титана, титановый сплав, на 3D принтере.
Понятно. А вот форма ячеек,
Формы
Соотношение, это размер ячеек, да, там соотношение толщины стенок,
Значит,
размер ячейки, это определяется.
это определяется природой. В первую очередь делаются акценты, что при полноценном... У нас есть такие два ограниченных условия. Первое, материал должен быть, казалось бы, поплотнее, чтобы он не разрушился, чтобы не было каких-то острых стенок. Но с другой стороны, и скорость прорастания тканей в мелких капиллярах будет гораздо выше. Но второе ограниченное условие – это при прорастании капилляров они должны снабжаться дальше
Сейчас вас не слышно.
витаминами, назовем их. А если будет капилляр очень маленький, то это снабжение витаминами, оно будет крайне затруднено. Поэтому есть минимально допустимый размер. На самом деле на сегодняшний день предложен достаточно большой спектр различных форм, различной геометрии ячеек, соотношения толщин. Коллеги из университета разработали ячеистую, это пересекающиеся шары с определенной долей, и мы уже занимались вопросом анализа их поведения под воздействием различных нагрузок. Ну и повышение
Спасибо.
стойкости изделия.
И можно еще один вопрос?
Пожалуйста.
Короткий. Когда вы говорили про металлокерамические композиты с высоким содержанием керамических частиц, там, до 50%, и говорили о том, что вы решаете проблемы их деформируемости, то есть обработки последующей. Вот, я не очень понял, как вы все-таки эту проблему решаете?
Значит, есть несколько вариантов. Если мы имеем высоконаполненный металломаточный композиционный материал, то для его дальнейшего формоизменения необходимо подобрать определенные напряженное состояние, скорость деформации, температуру. И оказалось, что этот материал достаточно неплохо деформируется в условиях так называемой ползучести высокотемпературной, когда скорость нагружения крайне мала, но она тоже еще не ползучая. То есть это под весом, постоянно приложенной нагрузкой, с нагревом происходит медленно процесс деформирования, формоизменения, и мы имеем полноценное изделие. В случае, если мы работаем синтезируем материал не исходно, грубо говоря, там, спекание, либо жидкофазные способы, при прокатке мы получаем готовые изделия и синтезируем изделия как раз в процессе деформирования. То есть исходное состояние – это порошки, а на выходе это лист с заданным комплексом свойств, где мы также играем с напряженным состоянием в очаге деформации и подбираем температурно-силовые условия воздействия.
Я думаю, что дискуссию можно завершить. Я предлагаю еще раз поблагодарить Ивана Сергеевича за удачно сделанный доклад и время, выделенное для дискуссии. Сейчас у нас будет презентация по скайпу. I have to announcement next speech. Professor Zhang, a Laboratory of Road Construction Technology and Equipment, Changshan University, China. Title of the report is Prediction of Small Specimen Fracture.
Okay, thank you very much, Professor Chairman. Can I begin now? Can I begin now?
Okay.
Professor Chairman.
Okay. And
Okay.
Where you are, please.
Share my screen. Can you see my screen? Okay.
Yeah, yes.
Okay, thanks again, Professor Chairman, for your introduction, and good morning, everyone. I would like to thank the conference committee and Professor Randchico for the invitation. It's my honor to attend this conference and make a presentation. The title of my talk is Prediction of a Small Specimen Fracture Pertinent to Material Construct, Microstructure, and the Relative Knot Size of a knot. It will be in 4 parts. The first part, I would like to introduce the model basis and the background of our research. The second part is the effect of material microstructure on fracture. The third one, I will introduce how to quantify the inevitable fracture scatter. And the last one, I will present and rectify the concept and its quantification in fracture prediction in details. The first part, as we all know, the fracture, the quasi-brittle fracture of a large plate with a shallow surface crack and tension, or a deep beam with shallow surface crack, and I used laser pointer. Laser point here. For a large plate with shallow surface crack and tension, or a deep beam with shallow surface and bending can be approximated by this equation. This equation is derived based on 2 fracture criteria. One is a tensile stress criteria. The other is a linear elastic fracture mechanics criteria, or the Kamantsev criteria. Based on the 2 fracture criteria and mathematical interpolation, we can get this single equation to cover both FT controlled fracture and Kamantsev controlled fracture, and the transition zone between the 2. As we all know, the linear elastic fracture mechanics is widely used and has been written in the ASTM standard. But to satisfy or to apply to the linear elastic fracture mechanics, some conditions should be satisfied. In details, the specimen thickness, initial crack size, and uncracked ligament should be larger than this value. And another extra condition is that the geometry factor should be 1.12. What does this extra condition mean? It indicates that it should be a shallow surface crack in a large plate. That is, A to W should goes to 0. Now the question is, what size of a B, A, W minus A are needed to satisfy the linear elastic fracture mechanics? A research team from maybe America, they calculate the detailed size for to use linear elastic fracture mechanics. They find that for a kind of grinder with average grain size 10 millimeter, to satisfy the linear elastic fracture mechanics, the minimum specimen width should be around 10 meters. As we all know that this size is unrealistic for lab test. Thus, based on this, we start our research. The second part is how to describe the effect of a material microstructure on fracture. Now let's go back. Now let's go back to the fracture curve. We can see that the two fracture criteria they has a intersection. This intersection is called as a characteristic crack. And this is a material constant because its value equals the 0.25 times K1C2FT squared. From this equation, we can see that different materials have different Kc and Ft value. Thus, the A/CH value is different, which may be due to the difference in microstructure. Here, we use the grain size. We assume the relative characteristic crack A/CH a constant. Thus, the fracture equation can be rewritten as follows. From this equation, we can see that the fracture stress, initial crack size, and the grain size can be measured separately for specific specimen. Here, through this equation, we can calculate the Ft value easily for any fracture of specimens. Now, if you carry out a number of measurements for different specimen or identical specimen, you can get a group of Ft value. Because Ft is a material constant, thus its variation should follow normal distribution. Thus, based on this equation, we can see that the Ft as a material constant can be linked to the average relative characteristic cracks. And through the mathematical analysis, we find that the standard deviation of the tensile stress reaches the minimum when the relative characteristic crack is around 3. To be precise, from 2.5 to 3.5. We use the specific measurement on ceramic materials based on the normal distribution analysis of tensile stress by changing the relative size at an interval of 0.25. And we find that the standard deviation of the tensile stress reached its critical or minimum value when the relative characteristic crack is around 3. And we also get the same conclusion when we analyze the K1C data. From the mathematical point of view, we continue to change the relative characteristic crack value and using 6 different measurements on 6 different ceramic materials, we find that the relative characteristic crack C is around 10. Thus, the fracture equation can be rewritten as this one. From this equation, we can see that it's only considered this the grain size, initial crack size, and this is material constant, which has a wide distribution. This is an analytical model, but by now we introduce the grain size into the fracture models. Again, these 4 figures show that the microstructure or average grain size has a significant influence on material properties like the tensile stress and the fracture toughness. That's why we introduce the grain size into the fracture model. The third part I will present how to quantify the fracture schedule. Just now I said even the material constant, like the tensile stress or fracture toughness, is not a constant, but has a wide distribution. This part I will introduce in detail. During data analysis of fracture measurements, there is a common phenomenon that the fracture stress is not a constant, even for identical specimen. That is, the size is the same and the material is the same. Thus, even at this extremely situation, the fracture stress is not a constant. Of course, this we can how to say, we can think that is because the fracture condition is not linear elastic fracture mechanics. But now, even for the linear elastic fracture mechanics, like the fracture of glasses, as we all know, glass is a special brittle materials because this is an amorphous materials. That is, the grain size is 0, at least in theory. Even for the linear elastic fracture mechanics, the fracture schedule is also not a constant but fluctuates. Now, the question is, where is the fracture schedule from and how to quantify? Here we list 4 factors. The first one is any material is not homogeneous. The second one is experimental error and machining error during manufacturing are inevitable. The third one, processing quality of a specimen is not a fix. For example, the surface roughness. We all know if rough surface there is a stress concentration, it should be an influence on fracture. The last one is environmental factor. For example, the temperature. Here, I take the first factor, the heterogeneity, as an example to explain why the fracture schedule is inevitable. A team in China carried out over 20,000 measurements on 2 classical steel. One is Q235, the other is Q345 steels. Their results indicate that the mechanical properties of a material is not a constant, but has a wide distribution. This is the yield stress. We can see that it's a wide distribution. Yeah, that's why the schedule is inevitable. Now the problem is how to quantify the schedule. In the part 1, I presented that normal distribution analysis is used to incorporate grain size into fracture schedule. Now we can use it again. With the normal distribution analysis, the mean and standard deviation of material properties like FT or K1C can be expressed with mean and standard deviation. Thus, the fracture equation can be rewritten as this. These equations include both mean value and upper and lower bound with 96 reliability. This can be used to describe the fracture schedule. Now let's see the result. With this proposed model, we can see that the model can well predict the fracture of specimens because the predicted curves with upper and lower bound can cover almost all the experimental data. Now we use the different 5 ceramic materials, silane, silicon carbide, alumina, silicon nitride with different grain size, we can see that the proposed model can well predict the fracture. In this equation, we can see that they only include the material properties and the initial size, grain size has no curve-fitting parameter. The proposed probabilistic prediction model can be expressed as a function of FT initial correct size, grain size, or the K1C. It's easy to change. In addition, it can also be easy to be linearized in application. We all know the linear is simple. The last one is the rule of relative knot size in fracture. Subsection 1, I will introduce the effect of a relative correct size on fracture. We all know that like the same length crack 1 millimeter, if the 1 millimeter in a big specimen or in a small specimen, its influence is different. As we all know, when you measure the K1C of a material using critical specimen, the critical stress intent factor or the maximum stress intent factor equals the fracture toughness of a material only when the fracture meets the linear elastic fracture mechanical conditions. Here we find that the K1C ratio is a function of relative correct size, based on the two equations. With considering the scatter, we incorporate the scatter by the tensile stress. Based on normal distribution analysis, we get this models. The Kc to K1C ratio is a function of only relative correct size. Now let's see the result. We can see that the predicted models can well the proposed model can well predict the fracture of specimens. Based on this figure and the equation, we can see that we can get that when the relative correct size A to G greater than 10 times 10, the ratio of Kc to K1C is over 95%. That is, the measured value of Kc can be regarded as a fracture toughness of a material. This is a linear form. Here we use the 4 different ceramic materials. We can see that the prediction has a good agreement with the experimental data. In this equation, we can see that this is an analytical models without any data curve-fitting parameter. In theory, it should be used to analyze the fracture of a different specimen with different materials. Here we put the 4 different measurements on different ceramics together. We can see that the proposed model can again well predict the fracture. Subsection 2, the effects of relative notch radius. If you measure the fracture toughness of a material using notched specimen, the notched fracture toughness or the maximum stress intent factor increase with root radius because when you increase the root radius, the stress concentration decrease. We proposed this model. The Kc to K1C ratio is a function of relative notch radius. As for this equation, from the mathematical point of view, if the root radius goes to 0, then this part is 0, this part is 0, Kcn to K1C. That is the notched specimen becomes a correct specimen. If the root radius goes to infinite, this equation becomes this one. That is the plane specimen. Based on the two extreme situation and using mathematical interpolation, we can get the single equation to describe all the parts. With considering scatter, we introduced a coefficient. Thus, we get this equation. Here it should be mentioned that during determining the mean and standard deviation of introduced coefficient, we use the normal distribution analysis and bootstrap sampling. We find that the mean standard deviation is around 1, and the mean value is around 1, and the standard deviation is no more than 0.15. Here's the result. We can see that with the proposed model, considering both fracture scatter and relative notch radius, the prediction has a good agreement with the experimental result. And from the equation and this figure, we get that the Kc to K1C ratio decrease with the decreasing rho 2g value. And when the rho 2g value less than 1, the ratio approaches 1. That is the measured value of Kc can be regarded as K1C. The subsection 3, combined effect of relative notch depth and root radius. Here, I would like to introduce 3 different fracture criteria. As we are doing, the fracture of a material is sensitive to a notch geometry, as the stress concentration is related to both the notch depth and the root radius. Here, this tensile stress criteria is for non-correct specimen, and this linear elastic fracture mechanics is applied to correct specimen, large correct specimen with shallow surface crack. And for notch specimen, we call the KT criterion. With the 3 fracture criteria, we proposed a model. This is a sigma into FT ratio is a function of relative notch depth and root radius. Again, to consider the scatter, we introduced a coefficient based on normal distribution and data analysis. We get the analytical models. Sorry, because time is up, I must go through quickly. With the analytical model, considering both relative notch depth and root radius, without considering fracture, we can see that the prediction has good agreement with the experimental method, and with considering the fracture scatter, we can see that the proposed probabilistic model can describe the fracture scatter. Now, to be easily understand, we can describe the describe the fracture, this value sigma into ft as one constant here, because this model considers two factors. One is relative loss length, the other is the stress concentration. If we separate them, here this figure is the sigma into ft variation with relative current size. And also, it can be used to describe the KT variation with fixed the A to G. Here, it should be mentioned that the relative size concepts can not only be used to analyze the quasi-brittle fracture, it can also be used to analyze the fatigue fracture. Here, we study the relative size of a knot on the fatigue limit for knot specimen. Now, we proposed analytical model delta sigma 0n. This means the fatigue limit of a knot specimen, and the delta sigma 0 is the fatigue limit of a correct specimen. Their ratio is a function of two factors. One is relative knot length or correct length. The other is the stress concentration, considering the root radius. We can see that the prediction has a good agreement with the experimental result. Subsection 4, the effect of a relative root radius and opening angle. In this section, the knot length is large enough. Okay? That is has a little significance on the fracture. Thus, we only consider the root radius and opening angle. We also built the relationship between this part and the two factors. One is the opening angle, the other is the relative root radius, because the IC is a function of a pi g. And we can see that the prediction has a good agreement with the experimental result. With considering the fracture scatter, we introduce the mean and standard deviation, upper and lower bound. The prediction can describe the scatter. Okay, here I list part of a publication about my talk. I put here in case anyone interested in it. If you have any question, my email is here.
Okay.
If you come to China after the epidemic, email me.
Okay, now we have some time for question.
Thank you.
Who has some question? Please do it.
Thank you for your interesting presentation. And you mentioned that fracture scatter is related to microstructure effect, and particularly with grain geometry. And what's about defects presented in the material?
Sorry?
Defects presented in the material, dislocations, pores, do they contribute to the fracture scatter?
Fracture scatter? Yeah, I think the fracture scatter is, how to say, is from several factors. One is the material is not homogeneous. The other, like during the manufacturing, the machining error is inevitable, and the main factor are two, in my opinion. Thank you very much.
Thank you.
We have some time for final question. Please.
Professor Zhang, do I understand?
Hello, Professor.
Do I understand correctly that you characterize microstructure by the only parameter grain size? Is it correct?
Sorry, again, please.
Do I understand correctly that you characterize microstructure by the only parameter grain size?
Yes, you are correct.
But but there is also distribution of grain size in the material. What
Yes,
do you mean when you use this parameter?
This in our research, we use the average grain size because the grain size has a distribution y, not a how to say, not a constant. So we use the average grain size. It's not very exact, but from the results we can see that it's better.
Okay, and the second question, in your formula, you use two material-related parameters, grain size and standard deviation of tensile strength. The question is, are these two parameters independent on each other? So,
independent? Which part? The last part?
I mean that when you use two parameters, grain size and standard deviation of tensile stress, this sigma beta, you consider them as independent on each other. Is it correct or not? What do you think?
I think it's correct because in each equation we use the grain size, average grain size to consider the materials. How to say? Consider difference of material properties. I think it's correct.
Professor Zhang, thank you very much for your presentation.
Thank you very much.
I have to close this section.
Thank you very much. And welcome you to Xi'an, China.
So, talking about high entropy alloys. Everybody knows about it. It's the last achievement of metal physics. And it is proved and justified of the gigantic knowledge, especially in very modern publishments. When we take high entropy alloys and use it as basics for printing, or for example, getting powder for more complex materials getting. So we integrate the alloys widely into industry. So this must be the basics for development of technology, both here and abroad. For example, starting from space, airplanes, protection instruments, energetics, everywhere. High entropy alloys are being used and are tried to be used. Now it's the first stage of these alloys use, and it's all about forming the systems with a steady structure, the mix of both structures receiving one-phase alloys and intermetallic alloys as well. So now I'm going to talk about these two examples and the usage of all the alloys used in different materials. We will try to understand the alloys that have viscosity more than high temperatures. So it's a regular story connected with the determination of high entropy alloys. Let me briefly represent it. It's about 4 or 5 elements that are hard to point out. All the atoms compete with one another, and there is a huge number of questions. Let's take classical alloy of Kant. All of them are magnetic, but that they get into an alloy, we get a huge problem. What happens inside with a thin layer when the magnetism is lost? And the cluster of formation from diffusion pressure. As a result, hardening of the process, it takes and requires more time to point out these phases. So this is what is known in these alloys. And finally, what we always talk about high entropy alloys, it's the famous counter alloys, allows to solve the problem of high elasticity with a high pressure and strain levels. So it leads to the thin nano couples, nano twins formation. And we don't include additional mechanisms connected with Martensic transformations. So 2 examples that we are trying to realize Martensic for deformations. So one of them is a thermoelastic Martensic transformation. So this is the model. And it's a big problem how to study this model. And there are more questions than answers, as it seems to me. I also want to talk about the first case. So it's the scheme which shows the richness of the phase when the favored in compression becomes favored in tension. So we are able to destabilize the material and learn the shape memory effect in them. And now we will be looking into this way. This is the dream of Georgy Vyacheslavyich Kutyumov to create alloys with elastic martensic transformation. They made a huge effort to understand what they had to do with the metal, which tests non-elastic martensic. So we can say that a lot has been reached, a lot of serious achievements have been received. So this elastic energy will save in the alloy without any manipulations. It's hard to do because of huge dimensional changes. So in order to take the Ellinger effect, to reduce the dimension change, this way gave us 2% of deformation, and there appeared a new scientific article they have produced an alloy which is high entropy. So why do we need here a Bohr? In single crystals, they lead to the fragile state of the alloy. So we want to have strong high entropy alloy. And thanks to Bohr, we can go it through the classical way, which is considered to be quite effective. Thus, when we talk about single crystals, we have a huge advantage because we have no grain edges. So the first criterion is realized through the strengthening of the material. And the second one is about reducing the volume change. Pay attention, please. At room temperature, the textured alloy gives 8.5% of strain. If you continue deformation, it can give up to 13.5%. It's very interesting. Because the metal used is not as costly as titanium nickel alloy. Although there is a catastrophe, when there is no texture, there is no elasticity. In spite of having bore, so this is our mutual work. So at this strain level, they don't want to be deformed. I would like to draw your attention to the following circumstance. So we can get it as a single crystal if the size of the grain is really huge. For example, 300 microns. And it can be worked out, the Martensic transformation connected with replacing from one net to another. And this source gives us 8.5%. But why do we have such deformation? So reversibility, this percentage, it's a huge challenge. Obviously, scientists started studying these alloys. An example how these alloys are used. A thin wire is received, the sizes of which are not big, from 20 to 100 microns. Further, we get oligocrystals. It's a crystal that has one direction, grain, the size of which is the same size as the pattern. And we can expect very interesting properties afterwards. And it is immediately shown in the following pictures. You can see how ideally the wires work. The superelasticity works in various temperature range from -50 to +50. So what do we have to do with single crystals? So if you have single crystals, you can plan, you can manage the potential deformation of the green depending on how much you are going to deform it. So these parameters are real numbers that depend on real parameters of the grid. So there can be minimum figures. And when straining, there is no twinning of the martensites. So we always need transformational twinnings when martensite transformations happen. And they can additionally go through the movement depending on having the component of twinning area. So the martensite can be both in twin state and the opposite, detwinning process. So we can see that the particles that keep the coherence they also lead to the martensitic transformation. So these are our data, changing the aging time and the size of the particles. We can get a wonderful elasticity with different ratings. So the question is seen on the screen. Can we compete with our Japanese scientists? And with this aim, we have prepared such material. Gigantic deformation. The common deformation is 20%, and the elastic deformation is about 14–17%. It's good with low temperatures. And the question is, why is the deformation so high? Here, a method of cooling has been created. Without this method, you will never understand what you have as a result of the transformation. So here you need to unload them, and you will see everything left there. And you will discover two types of twins. They are transformation twins, and they are closely related, and they're also mechanical twins. Which are considered to be non-native. So you can expect huge deformations, which will need a new scheme, which is about transforming the elastic twinning, and the whole process goes back in a circle. So at which state does the elastic twinning appear? This question is still open. Look at these beautiful, thick curves with high rate deformation. You can see how different are the properties when pressured and when strained. So there are some complex things. And further, we get the shape memory effect. Consequently, we can say that there is a very wonderful life happening here. And at the strain, we have such a picture. We have twin martensites. And finally, the picture that allows us to destabilize the martensite. My students like this so much, to work with it so much. So the idea is, okay, you can look at it at the screen. Unfortunately, it's not seen in the video. I wanted to show that if you stabilize the martensite, if you squeeze, press all this 15%, and to collect gigantic and energy, and then to free it, we get a blow-in transformation. And finally, I would like to show you brand new results when we use single crystals. When we have line phase and beta phase. So it's totally unexpected. We can see superelasticity and very unusual with the temperatures lower MF with martensite cooling. A martensite deformation is observed, and this is connected with the processes of elastic movement of martensite crystals with a thin structure change of these crystals. So concluding all my report, I'm showing you the pictures, and you can see that if we make up the structure of the particles of one type of particles, it's a classical AF interval and higher. And we have, if we have a double interval with high temperatures, in the interval MS and AF, and lower than MS to MF. And here you can follow the invertibility. There are two collectors of elastic energy, and the matrix call it the matrix of nano size, 3 nanometers, and the particles of beta phase, which are bigger, from 10 to 20 nanometers, quite big parts. So we have 2 stages. The first stage with gamma line phase and the beta, and the second with the beta line phase. And it allows to receive new and very wonderful things. It's quite an exotic topic, so I'm concluding. In fact, it seems to be really far. Perfect properties that we can get, and rows are also invented this way. And they are used in bridges and electricity transmission. And these Lego crystals got from these materials are potentially good for using as wheels for Mars research vehicle. So Mars rover goes and easily gets through. And concluding, I would like to say, I want to underline that in these systems there are so-called normal grain growth, so you can receive simple manipulations and single crystals, and there are very interesting, promising perspectives to combine printing of these materials with classical thermal mechanical transformation and to receive compound materials. This program is realized, studied in our common project, which we accomplished last year with the Karls University. And Leipzig University and some other partners of ours. When we were able to receive such wires and single crystals with unique properties that can be used in applications. I am done. Thank you. Question about the deformation character. Were there any experiments? So we are trying to strain 1x way and squeeze. Our colleagues from Illinois try to make different testings and experiments, as well as Texas University, and squeezing and straining the tubes and the pipes. And it's considered that these alloys can be used as highly strong. as particles in helicopters, and essentially simplifying the conditions for making the shape memory effect, and to be sure that the work which it conducts is included and generated inside the strain of these materials, and only changing the temperature, one can rotate this pipe with high rates, and which will receive the load as much in order to rotate this space. So it's quite a new direction in space, which is intensively developed with our colleagues in the US and Germany. And the high entropy alloys are going to find their usage in these systems. It may seem to be cheap in comparison with titanium alloy, but in order to go through this question, we need to make more effort, to think harder, to imply modern approaches to realize the properties that we require.
Вот, из Китая. Да. Нажать, слышно. Вот так.
Где наш профессор?
Нормально был звук?
Профессор Чан, are you ready?
Да, все хорошо. Все, можно сделать перерыв.
Потом еще.
Да, через...
Все, я просто включаю, дальше продолжаю. Да?
Здесь все прямо сейчас.
Все, прекрасно.
Можно выйти.
Удачи, профессор.
Несколько. Может быть, мы... Он без звука. Давайте тогда передвинем, пока он пытается настроить. А звука нет. Написал. Давайте пока это. Сейчас. Андрей Андреевич, есть уже? Есть. Да, давайте пока
Пока настраивает звук, послушаем доклад Синявский Андрей Андреевич.
So represent the center of protection of flights, which is in the heavy register version. So I'm going to show you a small story, how we fly on our planes, what problems we may get, not in the perspective, but of real life, and the problems that existed before today should be more or less considered. Particularly, I'm going to tell about problems which are connected with essential technologies, with titanium compressors, and I would like to show how we can manage these processes. In fact, as you know, airplanes have not one engine but two, and even if one engine is not working, a plane will be able and although the situation is quite dangerous, it's not the edge state. So at the beginning, I would like to remind you, those who want to get the book and know more about the topic, you may give us your address and we will send you the book. So the report that I am presenting is devoted to wave process of plastic deformation of titanium alloys, which is used in the mechanism of failure of compressor discs at different scales. So I mentioned before, it's very dangerous to let the engines go out of work. So in this case, it's 2006, and this is airplane An 124 Ruslan. It's dated June 2010, not really a long time ago. I'm also going to show you the crashed engine, which happened in 2020. So when we tell about the research that were conducted in a laboratory, it's better to see such examples no matter what experiment you are conducting and what result you want to get. So you can memorize, because each of you flies and will brightly remember these examples. So knowing the regulations of the crush, the testing should be held on time to avoid destruction or any defects which can lead to these conclusions. So the titanium alloys work with a specific parameters. So when we fly during 2-3 hours in some direction, we fly slowly, quietly, unless there is any turbulence, and we are warned to fasten our seat belts. So depending on the length, the titanium absorbs this load, and the validation period is essentially going down. So in realization law, we can see three different options. The first one is defective materials. The second option is about response rate under load. So after numerous considerations and statistics counts, we have come to the conclusion, in order to characterize any kind of destructions, you need to use the diagram of tiredness destruction. And the first state, it's meso 1, meso 2. And final is monocycle tiredness. And I would like to pay attention to the words that we use in comparison with research work. The terms are very important here. So we are used to saying microstructure, and if you say another word, meteorologists will not understand it. It's not a microstructure. It's a mesoscale. It's a mesoscale level. So it's a different scale level. The same about this diagram. It is considered that the disks of compressors work with a low tiredness. So what is few cycles? It's about the compressor which has changed the geometry, and what's going to happen with the engineer? It's going to disform. This is how we understand, and this is how we cooperate, but we need to formulate the reason. So if we say that the reason is low cycle tiredness, we will not understand each other. So it's about the high strain level. You will see it in one of the examples. So the classical materials used You can see the mechanic characteristics for the first and the second alloys. Classical structure of beta. It can be different structure, plastic or mixed type. So the destruction starts inside the grain. And from this point of view, independently, if one material is used or another, there is a common picture of destruction processes. You can see, because we have different size and big size objects, there is a big variety of the disk section. You can observe what difference is about material. The third mechanism of destruction, we have called them good, medium, and bad. The good one is when the destruction is the same mechanism. When we have trapezoidal cycle form, and when we have a triangle form, we have different surface. And the worst is the bed, the bed lay. So this type of setting is not employed anymore. It was used in the Perosian car. Different forms of cycles are shown here. So if we have bright the data which are about this that happened in 2009 2154, the catastrophe that occurred in Iran. So the delta shown here is the speed and exposure was 60 seconds. And unfortunately, it's going to be used in the future. So there can be used disks that can have these such dramatic consequences. You can see one of the disks of the airplane. Here you can see what I mentioned before. So this is one of the disks. It's a destruction, the catastrophe that happened in Iran. And another one is the disk in St. Petersburg. And fortunately, nothing bad happened as a result. So if we take traditional 20-second cycle, the loading of the disk, and then there is a crack with as 1 or 2 millimeters. And we can observe the following picture. So you can see the morphology of the lay. You can see how the sharp change of the relief morphology. Of course, it's a very steep change of the material, and it means that we need to somehow control the situation. So here is an example of the disk destruction. We have experimented that to define the structure. So when the crack goes along the texture, we have we can see the details of patterns under test. And these are the forms of cycles, the triangle forms and trapezoidal. So it appeared that the cracks in the patterns can be developed in different way. So the material chooses itself how to develop them. In some patterns, the cracks were moving as shown in this slide. We can see the fragile types as well as with viscosity types. And you can see the cracks along the whole surface. It's a crack development fragment. And this is the middle state. And then the bed state, you can see how the tunnels are made inside the dust destruction. And then there is in the cross direction. Analyzing all these processes, we have come to the conclusion. So what is happening in the process? Now we can see the process of formation of some fragile, but with others there is plastic deformation. So when we have the switch of viscose and fragile states, we can also see the mesotunnels when the crack goes first with the fragile parts, or when the crack goes across the texture, across these fibers. We see the smoothness relief, and it shows that these fibers also influence the material behavior. And a couple of words about the strain. As an example, we are going to look into the catastrophe which happened in 2020. So the disk split into two parts. So the situation was very close to the catastrophe. So the plane fell on the roof of a building, then fell down. And the crew of the plane did their best to land the airplane. And according to it, there was a task to get the strain level, to count the strain level. So you can see the area of destruction of the main material. Here are the parameters of the crack. 48 millimeters depth. So the development of crack was due to the fact of the section 1/10 depth when it was done when making the disc. So 60% of discs have such cuts inside. And when we tried to see what is happening on the factories where they produce these discs, we discovered that there was a fail while producing these discs. So imagine 60%. But this is about technologies. Now you can see peculiarities of the crack. And depending on our knowledge, we tried to count the parameters of strain. In fact, we have taken the resource that was realized while the disk was destructed. If we take the disk works with the strains lower than the elasticity of the material. We have taken the kinetic diagrams. So it's about strain intensivity and tried to calculate the coefficient of intensivity. And we have counted the level of strain. So the length is caused not due to general strain, but there is a reduction of the strain. Taking into consideration the concentration, we get into the level of strain which is lower than the elasticity. So in fact, the material has a high potential of disks, and the resource is many times lower that can be produced. Here you can see the fragments of destructing of the disks and an example how the crack, as we imagine, was derived. And here you can see the fragment of the disk, engine disk. And as a result of it, we have undertaken a mass experiment with high frequency tiredness of the patterns which were produced by the technology that I mentioned before. So unfortunately, there is a very high disperse, and it is connected with the fact that the structures are non-homogeneous, and with this parameter, the material can give 3 times with the formation of the crack, and unfortunately, it's a very warning one. And the place where we have the influence with a high frequency can be very essential, and the crack formation can happen not because of the criteria of meso level, but of a high cycle tiredness. So what we can see now, it's not very far from our future. And some conclusions that we have made concerning the questions that I realized can be read on this slide. Thank you for your attention. Gorgeous report as usual. The question is, the first stage of tiredness crack formation. How do these parts influence not the speed but the length of formation of the crack? The strain is very high. In that case, only these crazy non-homogeneous like 1/10 millimeters can be considered as heterogeneity that can cause cracking. So the heterogeneity that I showed here doesn't give that defect. So you have considered the risk. Are there any factors that are not identified by the specialist that can be identified in the future? So something that is not seen, you can't talk about it. So are there any other factors, defects that were not considered by the builders and the engine or disc producers that we still don't know. So I devoted to it the report. So I tried to show the process, the wave process of deformation essentially influences on the validation of the resource. So unfortunately, more than 12,000 or 16,000 hours, the disks were not employed. So concerning usage of single crystals in our and foreign engines, I know that a lot is paid attention to the pates of different systems. Are there any peculiarities of your approach explaining the single crystals? So when we talk about single crystal space, it's about 1 or 3 from 1 to 3 grained petals. And here we know that the technology unfortunately